Welcome back, Chemistry 30. This is the new unit, EC1, for electrochemistry. And what we'll be looking at here is investigate the chemistry of oxidation reduction, or otherwise known as redox reactions. So the topics discussed in this video, we'll look at EC1.1, oxidation reduction and oxidation numbers. And then EC1.2, balancing redox equations using the oxidation number method. And then 1.3, we'll be using the half reaction method. And then electrochemical cells, 1.5 cell potentials and spontaneity under standard conditions, and electrolysis. So this first part, EC1.1, oxidation reduction and oxidation numbers. What we're looking at here is explain what oxidation reduction reactions are. Use the rules used in assigning oxidation numbers to elements and compounds. Identify the substance that's oxidized, reduced, and the oxidation agent and the reducing agent. All right, so first of all, oxidation reduction. Reactions in which electrons are transferred from one reactant to another are called oxidation reduction reactions, or for short, often we just take the red part from here and the ox from here and refer to it as redox reactions. One of the most familiar redox reactions is the corrosion of a metal. So for example, below we have the Statue of Liberty there. It's a green. It was originally a copper color. A green coating forms when copper is oxidized. Also the Saskatchewan legislature, same thing. It was that green color too, and then before we put the copper plates on. A rust forms when iron corrodes. A black tarnish forms as silver corrodes. In some instances, corrosion is limited to the surface of the metal, with the green coating that forms on copper roofs and statues being one such case. In other instances, the corrosion goes deeper, eventually compromising the structural integrity of the metal. So for example, an old rusty car, it had gone through the surface and completely went through a metal door or whatever. So iron rusting is an important example. Corrosion is the conversion of a metal into a metal compound by a reaction between the metal and some substance in the environment. When a metal corrodes, each metal atom loses electrons and forms the metal cation. So the positive ion that metals tend to form when they lose electrons, which can combine with an anion to form an ionic compound. The green coating on the Statue of Liberty contains Cu2+, combined with carbonate and hydroxide ions, so from the surrounding air. The copper becomes the copper ion, so copper atoms, which make up copper as you know it, metallic copper, change into copper ions and then combine with negative ions found in the atmosphere and make a different substance. Rust contains iron, combined with oxide and hydroxide ions, and silver tarnish contains silver ions combined with sulfide ions. So in all of these instances, these metals, these atoms, lose electrons and thereby become ions. So for example, silver, a silver atom becomes a silver ion. And of course, it loses an electron in the process. When an atom, ion, or molecule becomes more positively charged, that is when it loses electrons, because remember, we can't add or subtract positives because they're held in a nucleus. So unless we have a nuclear reaction, we can't do it. So if I take an electron, so again, if a nucleus has 2 protons and there's 2 electrons circling around, if I take away one, it now has 2 protons and 1 electron, and that makes it positive 1 overall. So you become more positive by taking away the negative electrons. We say that it is become oxidized. So the loss of electrons by a substance is called oxidation. The term oxidation is used because the first reactions of this sort to be studied were reactions with oxygen. Many metals react directly with O2 in the air to form metal oxides. In these reactions, the metal loses electrons to oxygen, forming an ionic compound in the metal of the metal ion and oxide ion. The familiar example of rusting involves reaction between iron metal and oxygen in the presence of water. In this process, iron is oxidized, loses electrons, and becomes Fe3+. The reaction between iron and oxygen tends to be relatively slow, but other metals such as the alkali and alkaline earth metals react quickly upon exposure to air. The figure below shows how the bright metallic surface of calcium tarnishes as calcium oxide forms in the reaction. So over here we have calcium. Okay, so we have calcium, and if it's going to combine with oxygen, what happens is calcium is oxidized, and by that, of course, we mean it's going to lose electrons. So you can see the surface. So this is like a microscopic view here that's losing electrons. Oxygen is reduced. In other words, oxygen gains the electrons. So you'll have, so the surface calcium ions, they lose, so they become Ca2+. Oxygen gains, so they become O2-, so they come together and form CaO. So the surface of this would be calcium oxide. It's not easy to see from this diagram because it's in black and white, but you can see this is a slightly different shade than this because it's calcium oxide and not just calcium. So the calcium oxide solid forms on the top here due to calcium losing electrons to become Ca2+, oxygen's gaining electrons to become O2- ions. So in this reaction, calcium is oxidized to Ca2+, and neutral oxygen is transformed into O2- ions. When an atom, ion, or molecule becomes more negatively charged, so the oxygen, when you take in more electrons, we say it's reduced. So the gaining of electrons of a substance is called reduction. So when you have one reactant losing electrons, i.e. becoming oxidized, another reactant must gain them. So just like the transfer of money, if someone's losing money, someone else is gaining the money. And now there's an easy way to remember all this. You may wish to kind of sketch this out if you like. Get your artistic skills going here. And it involves, yeah, if you've guessed this is supposed to be a lion. Leo the lion says grr. I know the grr isn't spelled correctly, but that's how we can do it. So L-E-O, Leo stands for lose electrons, oxidation. So the loss of electrons is called oxidation. And over here, gain electrons is reduction. So you can use that little trick to remember which is gaining electrons, what's losing electrons. So Leo the lion says grr. All right. So before moving on, we have to look at oxidation numbers. So now we know what oxidation reduction is. There's something referred to as oxidation numbers we're going to have to look at. So before we can identify an oxidation reduction reaction, we must have a bookkeeping system, a way of keeping track of electrons gained by a substance being reduced and electrons being lost by another one when it's oxidized. The concept of oxidation numbers, also called oxidation states, was devised as a way for doing this. Each atom in a neutral substance or an ion is assigned an oxidation number. For monatomic ions, the oxidation number is just the same as the charge. So for example, on the previous page we talked about calcium. So it is very similar to the Ca2+. So it's going to have an oxidation number of +2. So we just write the positive on the opposite side. And we'll see it's going to, we need to know that in order to move on. So it's just simply equal to the charge. For neutral molecules and polyatomic ions, the oxidation number of a given atom is the charge that it would have otherwise. So if I have a sulfate ion, the oxidation number is just simply -2, corresponding to that hypothetical charge. For other things, we need to use these rules. So if we look at for an atom in its elemental form, such as looking at the periodic table, the oxidation number is always 0. So if you have an element by itself, it's just 0. So for example, if I have an H2 molecule, it's just simply 0. Each of the H's in there is 0. If I have a P4 molecule, each P is just simply 0. If I just have simply calcium by itself, it's going to be 0. Now this technically here, calcium, if I'm looking, I meant to say if I'm just looking at the calcium ion, it's +2. Okay, so for a monatomic ion is what we're talking about up there. But if it's just an element, it's just simply 0. Or sodium, it's simply 0. Oxygen, it's just, each oxygen is just simply 0. Okay. Now, as I mentioned up on the top of the page here, for a monatomic ion, the oxidation number equals the charge that it has. So monatomic ion, it's equal to the charge. So K plus, a potassium ion, its oxidation number is +1. The sulfide ion, its oxidation number is -2, and so forth. In ionic compounds, the alkali metals group 1A will be +1. The alkaline earth metals that are in group 2A are always +2, corresponding to their 2 positive charge. And then group 3A, such as aluminum ion, Al plus or 3+, will be +3. In writing oxidation numbers, we write the sign before the number to distinguish it from the charges. Right, I think we'll stop there. We'll come back and we'll move on to the rest of the oxidation rules.